attendance. We're excited to kick off this webinar series with a talk by Qing Zhang, our software systems manager here at BSI. And this talk is titled From Discovery to Validation, PEAK's DIA Solutions for Proteome and Peptidome. In today's session, we'll dive into the latest developments in our PEAK Studio 12 software, focusing on our powerful DIA workflows that address the complexities of DIA methods, where multiplexed MS-MS spectra from multiple peptides can pose challenges for accurate identification and quantification. Qing will show you how PEAK Studio 12 addresses these challenges with advanced deep learning algorithms for peptide identification and quantification, ensuring comprehensive proteome coverage and enhanced FDR control. Additionally, we'll explore unique solutions for DIA immunopeptidomics, as well as our cutting-edge hybrid DIA-PRM workflows that merge discovery and targeted proteomics in one seamless solution. We ask that you please stay muted for the duration of the webinar and save all questions until the end. But I guess without further ado, please welcome Qing Zhang to guide us through these cutting-edge advancements and how they can enhance your research. Let's get started.
Okay. Thank you, Brandon. Let me share my screen. Okay, can everyone see my screen now?
Yeah, we can see it.
Okay, thank you. We can get started. So welcome everyone. So today we will talk about the PEAK DIA solution. So for today's topics, we'll talk about this from the discovery to validation. Since now in the PEAK 12 in our DIA workflow, in fact, we can support both the discovery, something like the general DIA workflow, and also the validation includes, we have the PRM workflow, and also the hybrid DIA workflow. And also today we will show our workflow or our solution for the general proteomics and also the peptidome. Okay, so first, just I did the brief introduction to the PEAK's product lines. So we have 4 products. We have the studio and online. It's mainly for the general proteomics and the peptidomics. And also we have our glycofinder used for the glycopeptides identification and quantification. And also for the industry customer or those who focus on the antibody, we have the PEAK-AB for the antibody characterizations. Okay, so we can start today's topics. So today we introduced our PEAK DIA solutions. So we will introduce these solutions in two levels. The first level we can say is on the function level, just like in our rural research. We will usually have 2 steps. The first step is the discovery step. We do the discovery proteomics to find the differential protein or the differential peptides. Then we will do the validation, usually it's the PRM. And also now we have the hybrid DIA, so we can do in one round, we can do both discovery and the validation. And then we just based on the application level. So usually with the general proteomics, usually we focus on the protein or or call it the proteome. And then we have our workflow for the peptidome, focus on the small peptides, especially for the HLA peptides, those non-specific peptides. And then we have time just to have the software demo, lab demo to show the function of our software. Okay, so first, before we start, we can have a brief introduction to the PEAK's product. So for our product, for the general proteomics, especially for the studio and online, I think this is some unique features for the PEAKs. The first one is that we are vendor neutral. So by now we support our DIA solution, support most of the vendors, including the Thermo, Bruker, Sykes, Others. And then we have the UI to help you to evaluate the data, to offer you different figures to evaluate, okay, if this result is good or confidence identification. We support both the DDA and the DIA data. And from the PEAK 12 now, we have the discovery phase and also the target phase. We have the DIA and the PRM workflow. And also this is the same, all our workflow, we hope that we give you the accurate and the sensitive results. And also now most of our workflow will have the QC steps to help you control the result and validation the result. So today we do a base focus on these two parts, the DIA and the hybrid DIA, including the PRM. Okay, so we can start from the DIA. So we know that in the recent years, so more and more people will select to use the DIA instead of the conventional DDA or the PRM. So this is we searched the publication number in the PubMed. You can see in the recent this is in the recent 15 years. You can see after something like after the 2014. You can see the trend is that it is significant. More and more people will use the DIA. Also, there are a lot of the review papers to discuss why we select the DIA instead of the DDA. So basically, I think there are some advantages for the DIA acquisition. So in our BSR website, we also list some of the features also some of the advantage for the DIA. So, but I think if if long in short, we'll say that for the DIA, it gives us more about the reproducibility, the data completeness, and also the due to the sensitivity, it will give you more the protein coverage or sometimes we call it the sequencing depth. And also, this also means that in the DIA data, we will have the less variance and also the less value. So that means this is the advantage of the DIA acquisition method, but also this means that how can the software show this advantage of the DIA method? So that's why we have the DIA solution. So I think this is a very good paper in the last year. The Professor Shui, they discussed a lot of parts of the DIA parts. So here they list something of the DIA data process. So I think whatever the software you use, usually we can divide the DIA analysis into two parts. The first one we call the spectral first, or usually called the spectral centric workflow. That means we start from the MS spectra. We try to generate we call it the pseudo MS2 scan. Then we convert the DIA data to the DDA data, and then do the normal DB search to get the result. This is the spectral centric workflow. The other one is we call it something like the peptide centric workflow. Something like here, we input the peptide faster, and then we can do the prediction. We predict the MS2 spectra. Then we do the search. This is called the peptide centric workflow. So this is two workflow. So talk about the peaks. So what's the unique features for the peaks DIA solution? So the first one is that we always say that we are the streamlined workflow. So why we say it's the streamlined, we can say here. For DIA data, usually we start from the spectral library. If the user input, we have a spectral library, we will do the spectral library search first, then do the FDR control, get the peptide list from the spectral library. So this step is optional, since now more than people, they say, okay, spectral library is good, the quality is good, but it's time consuming. I need a lot of time to do the fraction to get the result. So more and more people will say that, okay, I don't want to use the spectral library. I just use the library free method, or here we call it the DIA-DB search. So here is the same. If it's the DIA-DB search, we still start from the DIA raw data, but the input is just the protein database. Then we do the DIA data database search, do the FDR control to get the DB peptides. And then we combine these two parts to do the quantification. And then now we have a new step we call the quality control, the QC step, to control the result, to get the final the identification and the quantification result. And also in here, we have additional steps here. If it's also optional. If the user are interested, okay, my interested peptides may not in either in the spectral library or in the database. Then how can I find it? Usually, in this time we will recommend that okay, we can do the DeepNovo search here. So for the raw data, we can do the de novo search and do the ALC control to get the final result. In here, this in fact, in last year or in the new Peptide release, we have a new workflow. It's the graph novo workflow. In the graph novo, in fact, we can do the FDR control for the de novo result. So if you are interested, we have the paper list in the last page. You can check that papers to see how can we control the FDR for the de novo peptides. Okay, then this is our workflow for the general proteomics, and also we know that a lot of the user, they are focused on the small peptides or short peptides, not the protein. So we have our specialized workflow for the peptidome search. So basically, if the input is the DIA data in the Peptide, we have 3 workflows for you to select. So the first 2 just for the general proteomics. We can do the identification only, or do both the identification and the quantification. And then we have a peptidome workflow to design for the small peptides. Okay, then after discussion before, so we know that for the DIA data, we want to show that it have the high reproducibility, it have the high sensitivity. And also we want to show the quantification performance, something like, I know the HY data, I know the known ratio. Can this result give me the correct ratio? And also we want the data completeness to see how I can find most of the sample in most of my runs. Okay, then in this case, so for the software, what can we do? So now in the software, usually we have several steps to help you to reach these goals. The first, I mentioned before, is the streamlined workflow. We combine the spectral library search, database search, and the de novo result. And then we have the match between run. In before, the match between run only in the RFQ steps. So now we move these steps to the identification steps to increase the data reproducibility. And also we have new options for the quantification mode. You want to quantify them more, or you want to quantify more accurate. And also we have to upgrade our AI-driven predict to predict more peptides or use the less time. Okay, then here is the example. So the first thing we say that how can we increase the sensitivity? Besides the prediction, we will discuss later. The first thing is that since we are streamlined the workflow, we combine a different strategy to get the more result. So here is the example for DIA data. If I have the spectral library, you can see that, okay, spectral library can find these peptides. And based on this result, we can do additional database search. You can see that in the DB search result, it can give you around 10% more results, which means these peptides are not in the spectral library. And also, based on these 2 results, we can do the de novo search. You can see that. So for this de novo search, it gives you around 2% more of the results. That means for these peptides, they are not in the protein FASTA file. So we combine these three results to give you the more results to increase the sensitivity and the data completeness. Also, then the second step is called the reproducibility. So we put this step here. So now there is a checkbox here. You can use either use or with or without the match between run. So this is the comparison here. You can see that without the match between run, for 3 technical replicates for our DIA data, in the middle it's around 82%, and for each replicate, they have the unique peptides. The ratio of the unique peptides is still larger than 1%. Usually, this is acceptable for the DDA data, but for the DIA data, usually we are more strict. We want to say that, okay, this number should be less than 1%. So you can see here, with the match between run, this ratio will decrease. So, and the overlap here is more high. So that means with the match between run, we increase the reproducibility. And also now we have the two mode for the quantification. You have the precision mode and the accuracy mode. So what's the difference of these two modes? Here is the example. So this is a classical, the classical HYE data. So we know the ratio for the human, yeast, and the E. coli. So it's clear to see that if I use the accuracy mode, and in the final result, the ratio for the human, yeast, E. coli is close to the real ratios. Okay, this result is very correct. The ratio is correct. And for the same data, if we use the precision mode, you can see that, okay, for most of the protein, since for the HYE data, the most of protein are from the human. You can see that, okay, human is still correct. The ratio is correct. But for the yeast and for the E. coli, you can see that there are some bias here. The ratio is not correct. Okay, and so we know that, okay, in this case, it's better to use the accuracy mode than the precision mode. And in here, someone maybe will ask, why we not always use the accuracy mode for all the data? So you can see here, this example for the same data. Besides, we compare the F2 ratio, or we compare the quantification accuracy. We also compare compare the precision, or we compare the protein CV. You can see that although in the accuracy mode, to give you more accurate the result, but the CV is higher. Something like in some application, we are more focused on our precision. We want to that, okay, I want the reproducibility is high. The protein CV should be less. So in that case, you can see that we will recommend that we still use the precision mode to get the better result. Things for this, it's a trade-off between the precision and the accuracy. Okay, you cannot get the both high in two ends, so it's a trade-off. Just depends on your application. You can select the either mode. And then the final step is the data completeness. So I like the figure and this paper very much. So it's very easy to understand how is the data completeness. So that means for something like in one experiment for one protein, how many for this protein it's found in how many the ratio of in all the samples. So if one protein is confident identified and quantified in most of the sample, then the data completeness is very high. So basically, this is the basic requirement for the DIA result. We should have the less missing value and the more reproducible and the correct quantification. So to reach to achieve these goals, we upgrade the prediction model. So before our prediction model only supported the limited number of the PTM. So something like we only support the oxidation since it's very common. We don't support the phosphorylation or other the uncommon PTM. So now in our model we can support all kind of the PTM, even it's not being seen in the training model before. And we input the peptide sequence, include the PTM, then we will do the prediction. Usually when we predict three paths, the first one is the MS2 spectra. We can predict the MS2 spectra and compare the predict MS2 spectra to the measured MS2 spectra to see the similarity between these two. And also we'll predict the rotation time is the RT, so to see if our result is the correct. And also if it's the ion mobility instrument, we can predict the CCS value to see if the identification is the correct one. Here is the example of our prediction. So for the MS2 spectra, usually when you get the result or you check the result, we will have this figure. We call there's the mirror plot. So in the top of the one is we call the query. It's the measured MS2 spectra, and then in the bottom is the predict one. So you can compare these two to see if they are very close. And also in here we will give you we call the unmatched tables. In here, you can check the predict MOV, and the most important is the predict the relative intensity to see if we can cover the most of the peak and the most abundant peaks. And also we have predict the RT. So for the RT, we offer you the result in two levels. One is under we call it the project level. So in the result, we will offer you a figure. So in this figure, we will give you the delta RT value in each of the LCMS time range or the interval, something like for all your LCMS time, we map them to the IRT, and we calculate the delta RT for all the peptides, and in a one small range, something like the timeliness interval. So we will know that in which part the delta RT is large or which part the delta RT is small. We can see and to see if the result is confident identified. And also for each peptide, we offer you the result in the peptide level. So in the peptide result, for each peptide, we will have additional column, the delta RT. So we can know that for these peptides, what's the difference between the predict RT to the measured RT. And also in the peptidome workflow, we also offer you this histogram to show the delta RT and the regression line to help you to see, okay, if this result, even in this regression line, or even will differ if it's found by the DB search or found by the DeepNovo search. And also if it's the team source data, in here we also will offer you the figure for the CCS value. Okay, then combine all of this result, we will have the final result. So this is the example of DIA match in our DIA search result. So assume these peptides, we will list the sequence, the score, so we will list the score, and some other attributes related to the peptides, including the mass, length, and the mass error, the MOV RT, and here we will offer you the delta RT here. And for each peptide, we will list the peak area or it's used to the quantification. So for all the DIA result of our area come from the MS2 spectra. And then in the bottom, we will offer there are three parts of the figures. So in here is the MS2 spectra. So we offer compare the matched MS2 spectra to the predict spectra, and also we can find the sequence in the fragment here. And here we have the AND table to tell you, especially if we want to compare some very small peak or very large peak. We compare the intensity, the predict the relative intensity here. And in the middle, we have the feature view. So just for this one, just to tell you the retention time and the MOV in a 2D geo view to help you to assess, okay, if this result is good. And also in here, we offer you the XIC, the extract chromatin graph here. So in the top is the MS1, in the bottom is the MS2. So we can check if the first something like for this peak, if it's the symmetric, and also you can change the number of the fragment ion here to use if we want to use more or want to use less fragment ion here. Okay, then now we can show some the demo result or the benchmark result. So the first one we show here is from the Orbi Astro, from the paper from the Professor Olsen. It's the first paper report that they used the Orbi Astro. We used HYE data, and the input one we used the 200 nanogram to show the performance. So to do this search, we just show here is just in our DIA workflow. So we selected the DIA workflow, And this is the DIA-DB search parameter. So we just input the very common search parameters here. It sets the enzyme and the digest mode, sets the PTM and the number of the PTM, and then input the FASTA file, input if something like we want to remove some protein from the contaminant, we just input the FASTA here. And also in the result, we offer you two options. In here, we call it the sample-based or the project-based. So sample-based, it's something like others, they call it the local FDR. So that means if you in one analyze, we have a different sample. So in this one, we will control the FDR in each sample level. That means for each sample, their FDR is 1%. But that means their cutoff may be different, but maybe different. So here, when you select here, you can use we recommend that you use the value 20. So if the score is 20 here, that means for each sample, we control the FDR in the 1%. And also you can still use the project level FDR. So if you select here, so that means in the project level, so the total of the final FDR is 1%, but that means for each sample, maybe their FDR is not 1%, since especially for the clinical sample, each patient are very different. So on the project level, if it's 1% FDR, but for each patient, it may not be the 1%, maybe someone may be higher, or maybe someone may be lower. And also then in the protein level, we just offer one option. That means in the project level, you either use the protein FDR, or you still prefer to use the score to do the cutoff. So this is the basic search parameters for the DIA search. And then we can check some of our result. So basically, in our result page, there are two parts. In the left is the result node. It will list the result from each steps. So you can check the result in each step just by double click this result node. You can open the result. And in the right is our result page. So usually for each node, we will give you two or three pages. So the first one usually is the summary page, and then we have the protein page and the peptide page to tell you the protein and the peptide result. So in the summary page, first we will have these two figures to help you assess the result, the quality of your result. So the first one is the sample-based the FDR curve. We will use the first sample to draw this FDR curve to help you to assess the result. You can see here for this FDR curve, we cut off the score 20. That means the 1% FDR. Okay, you can see okay. This cutoff should be reasonable since the cutoff is in this region where the change is large, so it's reasonable to cut off here. And also we check the RT regression line to see if all the results they are fit to this regression line and they have enough points here, or enough data points here. Okay, we can say okay, this result should be good since these two figures tell me that okay, this identification result should be good. And then we can also check the delta RT across all the LC time. So we know that usually in the start of the gradient, the system is not stable yet. So only in this region, or maybe in the end, the delta RT is large. In the middle of the LC time, you can see that all the delta RT is very small. So that means our identification result should be good. And then we will give you the statistical tables to list these numbers for all the project, or from all the sample, or from each of the one sample to help you to assess the result. And then here we also will give you some basic information, something like the PTM size and the filter, the cutoff value for the result. Then here we will have the protein page and the peptide page. So the protein page is the classic the PICS viewer. We have the the accession number. In here, I add a new column is the gene. So it's easy for the user to do the downstream analyze, just to use the gene name here. And also we have our classical coverage map here. And then for the peptide result, just like we showed before in the peptide result viewer, will give you the peptide information, the mirror plot, the feature view, and also the XIC to help you to assess the result to see if this identification result is good. And also for the LFQ, basically it's the same. We have the 3-page, have the summary page, protein page, and the peptide page. The difference is here in the LFQ page. By default, we have this volcano plot to tell you which protein are up regulated or the down regulated here. And also especially for the HYE data, we have an option here is the density ratio plot. So we can easily get the density ratio plot to see, okay, if my LFQ ratio is close to the correct value. And then it's the protein page. Basically, it's the same as the identification result. There are some additional column in the LFQ path. One column here is use the color schema to give you the idea of the protein is the upgrade or is down regulated here. And also we have the additional volcano plot. So in PIX12, they are upgraded here. In before, we only allowed if you have multiple groups, something like if I have 3 groups, we're not allow the user to select which 2 groups to compare. Now in PIX12, we have this option here. If you have 3 groups, you can select any of the 2 groups here to generate a new volcano plot here. And then it's the peptide level. Basically, it's for the peptide table is the same as the DB result. You have additional column here. Use the color schema to tell you the ratio in each sample and in each group. And the difference is here in the LFQ result, we show the XIC here. Usually the top is the MS1 and the bottom end is the MS2. And then here you can select a different sample. In the design, we allow the user to show the maximum number is 4. In the same time, you can see you can show the minimum number 4 of the XIC in one time. So in here is the HY, so you can know that this is the sample from 2 groups. Because you can see clearly that for these yeast proteins, the first group, the ratio is close to 4, is something like 4 times larger than those in the second group. Okay, then we have an example for the TeamSoft data. It's the TeamSoft from the TeamSpro2. Since the paper is still not published, so we just connected the author. So thanks for the Dr. Liu and the Professor Sun. They share the benchmark result with us as the reference. So this is their own result for the TeamSoft data. And then we can compare the result to see, okay, for the human and the yeast, the correct one. So for the E. coli, in fact, both of our benchmark to show that they are a little biased here. So I think this is still acceptable. So we know that, okay, the result is good. And also, we also support the DeepNovo data. So this is a benchmark result from the paper. We used one of their data is from the Xeno source. The optimized isolation window. We use this data set as the benchmark. So looks similar. You can see. So for this one, it's very interesting. You can see that in the paper, both of the E. coli ratio have some bias here. But you can see if you check the result in PIX12, the E. coli ratio is still the symmetric here, and also the ratio is correct. So this is still to say that the PIX12 performs better in this result. Okay, in before we show that how can we in the discovery steps we can get the discovery result to get the the differential protein. Then usually in the clinical research or in our real research, then next step we need to do the validation. Usually we can have the cohort sample here and do the DIA search to find the differential protein. Then we need to do the validation use the PRM. So that's why now in the PIX12 we offer our PIX-PRM workflow to help you to get the result. So due to time issue, I will not introduce the PRM workflow, just to show some of the results. So based on the calibration curve, we can do the absolutely quantification. And also it's the same. We use the MS2 frame ions to do the quantification. Okay, and then we introduce this is the very new technical called hybrid DIA. Since before we mentioned that in the real search or the clinical search, we need to do the discovery and the validation. But we know that sometimes the sample is the amount of the sample is very small. And usually, if I get the sample here, and most of the sample we need to do other things than the LC mass. So for the LC mass, only a little of the sample here. So if I want to do the discovery and the validation, is there a way I can do both the discovery and the validation in one run? This is the question. Also, this is the thinking why the authors they developed the hybrid DIA workflow. So basically, we use a data set from this original paper, still from the Professor Olsen, and they work with thermal to develop this method they call the hybrid DIA. So basically, it's the DIA plus the PRM. So in the DIA run, if we find some triggered peptides, usually triggered peptides, we will trigger the PRM scan to do the PRM quantification. So if you are interested, you can check this paper for more details. So for our benchmark, we use a data set from one of the experiments. So in this experiment, we start from the human cell line and do the phosphorylation enriched peptides and the spiking some internal standard peptides. Use these standard internal standard peptides to trigger the PRM search. And to want to compare that if the hybrid DIA can do two things. The first thing in the PRM part, if the hybrid DIA can find more the triggered peptides or our interested peptides, since these peptides are usually the marker. And the second step is that since hybrid DIA can also do the DIA, can the DIA part in the hybrid DIA get the comparable result with the conventional DIA search? Okay, then here we show this the PIX hybrid DIA workflow. So since it's the DIA plus the PRM, so the search parameters or the layout is very close to our DIA and the PRM page. In the DIA, it's the same. This page just almost the same, just setting the search parameters for the DIA search. And also here in the PRM workflows, the first thing that we select the labeled method for the triggered peptide. Since for this paper we use the select, so we use the select peptides here. And here we will include the triggered list. So for here the example of the triggered peptide list, we will tell the software, okay, in which retention time, in which M over Z, we will, and it's which peptides. Then we will do the PRM quantification for these peptides. So this is basically the result in the PRM part of the hybrid DIA result. So we can see that in the PRM part, most of the peptides can be found. Only those very low intensity, you can see that even the PRM cannot find these peptides. And we are more focused on the ratio since this step is something like the PRM. So for the PRM, we know that if we compare the PRM to the DIA, PRM will perform better in the quantification and the dynamic range. So we can see here for these peptides, this is the PRM part. The ratio should be, since this is 3 groups, so it's the 2.5, 5, and 10. So the ratio should be 1, 2, 4 here. So we can see, okay, so for this peptide, PM get a very good result. The ratio is close to our real ratio. And also we can check that these 2 samples here. You can see we used MS2 to do the quantification. For this one is the normal, is the heavy peptides, is the internal standard. So they are very high, and their intensity is close, and we will do the normalization based on this heavy peptide to get the final result, of the endogenous peptides result here. Okay, so this is the hybrid, the PRM part. And then we'll compare that if in the DIA part, in the hybrid DIA, you can get the similar result to the DIA search. So here I just use the Venn diagram to show the result. This is the peptide overlap. Here is the protein overlap. You can see that for the hybrid DIA, the DIA part can still get the comparable result to the conventional DIA. So that's the value of the hybrid DIA. We can do the discovery and the validation in one round. Okay, now we can talk more about the peptidome, since we know that for the general proteomics, we more focus on the protein level. And in the peptidome, we are more focused on the peptide level. So compared to the general proteomics, the peptides, they are small. And sometimes, especially for the HRA peptides, they are unspecific digest. So for the search, we need to focus more, put more attention to control the FDR result. So here I just show some the benchmark result. So the first one is from the thermal instrument. We have the RA957 cell line for the DIA data. So in the original data, we have the DD and DIA data. They use they use the software to get the result. And also 2 years ago, Professor Mann, they published the alpha peptide, use the same data set, but use their deep learning model to do the search. So we compare our result to the alpha peptide here. For the search step, this is the same. This is very close to the DIA-DB search. The only thing here to be noted here, usually for the HRA peptides, we know the long distribution. So we'll input the range here to get the to reduce the search space, and the same for the quantification. So here, this is the result. So we compare our paper result to the paper. You can see that our result can report more sequence, and we can cover around 87% of the paper's result. So for this part, how can we know this part is the correct one? So we can do 2 comparisons. The first one is the peptide length, the distribution. You can see that both our results, their distribution is fit to the HRA and the HRA1 peptides. And also, peaks report more peptides in the NIMA here. So this is our expectation, since we know that for most of HRA peptides, the peptide length is 9. And also, we compared the binding ratio here. You can see that for peaks 12, we report more results. And even for the binding ratio for this NIMA, they are also very close, around the 97 or 98%. So that's based on this, we know that okay, peaks report more peptides, and also the result should be the correct one. And also here I show you an example. So from the Professor Bassani Sternberg's. It's the peptides, it's the non-canonical peptides from the circular RNA dia of the peptides. So that means these peptides usually are not in our canonical FASTA file. So we want to know that if our DeepNovo can find this kind of the peptides without something like without the RNA-seq data. So here I show you an example. So for these peptides, it's from the non-canonical. It's the circular RNA dia of the peptide. So it's sequenced not in the canonical FASTA file. I just use the human canonical FASTA file as the input. So you can see that DeepNovo can report these peptides, and based on the mirror plot, based on XIC, the identification result is good. So this shows that okay, DeepNovo, the DeepNovo is a very good alternative to help us to find the non-canonical peptides. Also here we have an example for the timsTOF data. This is the data from the genetic. So they develop a method and evaluate the method based on the timsTOF instrument for the HLA peptides. So here we just use the same data set, the 4 replicates to compare the result. So here I just show since it's the method evaluation. So it's very easy to use our QC function to compare the result. So here I just show that in the QC function, it's easy for me to check, okay, for all these 4 replicates, how many peptides are identified. And also here I will have if you click on each row, you can compare the overlap between the 2 replicates. Okay, now here the summarization. So for the PIX DIA solution, we have some unique features. The first one is that we are the vendor nature. We support most of the vendors. And also we offer the workflow from the discovery, include the discovery and validation. So from data type, we support the DIA-PRM and the hybrid DIA data. And our workflow support the proteomics and also the peptidomics, or more people may use for the immunopeptidome. And all the workflows are driven by the AI technical and something like the prediction. And now all of our workflow we offer the QC steps. You can use the QC to control the result. Okay, and here are some the paper from the BSI, from the BSI in the recent years. So if you are interested, you can check these papers. So now there are 2 ways to check these papers. The first is in our BSI website. We will list our users' publication, and also for each week we will offer some the publishing here. And also in our software UIs. If this page will be upgraded automatically to give you more information about what happened in our software. Okay, so basically before we go to the software live demo, so next week is the HUPO. So if you are interested, just come to our booth. Our booth number is the number 14 in the Germany, and also we have a breakfast seminar. So during this seminar, we have 2 speakers. So Professor Wei Wu will tell us about the immunopeptidome research. And also the professor, the growth, they will show us the results from the hybrid DIA, since their work is on the cancer sample. They use the hybrid DIA to analyze the cancer sample. So if you are interested, please feel free to register for this breakfast seminar. Okay, then we can go to the software demo, just to quickly show our software UI. Okay, so here I just basically show that there are some buttons or new functions in the PIX12. So for the full workflow, this part is the same. We just upload the data. Then we can select the enzyme, the instrument, and the fragment type. And also here we always use the DIA. So here now before we only support the DDA and the DIA. Now in here we'll support the DDA, DIA-PRM, and the hybrid DIA. You can select the data type here. In the workflow basically the same. And here we just search in the search parameters. And here is the DB search result, and then we have the quantification results. Okay, let me just go to here, and here we have the quantification mode. You can shift between the different quantification mode. And here we use the QC, okay. And then we have the QC steps and the result filter. You can select use the sample-based FDR, or it's the project-based FDR. And click finish, you can go to see the result. So here I just show you some UI here. For the summary page, you can see this curve, this FDR curve, this regression line in the summary table. And in the protein wheel, you can shift between the different protein to check the informations. And also this is the peptide page. You can see the the mirror plot and the XIC to check if this result are reasonable result. Okay, I think that's all for today's webinar. So if you have any questions, you can just talk to us now. Let me check if there are any questions in the Slack channel.